So iron basically forms in one of the stars, but that is the end of stellar nucleosynthesis. Like that is in the fusion cannot produce more stable elements than iron, because the stellar nucleosynthesis is basically governed by the stability of the nucleuses, like the nucleuses that are produced. So it stops at iron because iron nucleus is the most stable nucleus. Okay, so you cannot form a nucleus which is more stable than iron. So it drops. But that doesn't mean that you're not forming these other elements. You do form it, but with different processes. Okay, so iron is like really stable, and that is why it forms like a huge part of our Earth. So iron forms huge chunk of the Earth, at least. Yes, the bulk Earth. I have this written down. Yeah, so the bulk Earth composition is something like this. This is the symbol for Earth. This is like the equator and the prime meridian, so that's why how we show it. For Sun, it is like this. Mars, it is this. Venus is this, things like that. So bulk Earth, iron, oxygen, magnesium, silicon, sulfur, nickel, calcium, and aluminium. There are others, but these are this is the maximum, like this is the by weight. This is the most abundant element on bulk Earth by weight, iron. And most of it is in the core. So now, so iron is in the core, nickel is also in the core of Earth. This is not true for this might not be true for other planets. Mars has a lot of sulfur, and we might discuss this, but we'll definitely discuss it in my planetary geochemistry course if you guys take it. So oxygen is the next one. So this oxygen is in the crust. Now also there is a lot of silicon available, magnesium available, calcium, aluminium. So all these are forming a huge part of the crust. Now, silica or silicon, Si, has this property called catenation. Which is similar to carbon, in which it forms these different kinds of like chains. So silicon also forms chains in this shape. So you'll form a lot of minerals, a lot of compounds that will have this as the basic structure, and then we'll have all the other things, magnesium, calcium, aluminium. So you can have magnesium silicates, you can have calcium aluminium silicates, you can have iron silicates. Where do you think you'll have more iron silicates? Near the core or in the crust? More iron silicates, iron and like compare iron versus calcium aluminium. Where will you get more iron-rich silicates? In the crust? In the core or in the crust mantle? Near the core, right? So as you go closer to the core, because also iron is very dense, that's why it's also settling inside. So another question is like, why do we have a core? I mean, it's basically density. So imagine the entire Earth was molten, and then we call it differentiated. So this is the term that is being used. The bulk Earth got differentiated into crust. So this is the crust. We have a core. And we have the rest is the mantle. So the crust is like really thin. 7 kilometers, like average. Okay. The mantle is like the bulk that exists. Okay. The core is like iron. So when you have everything molten, everything will be gravity separated, density separated. So the things that are the most dense will fall towards the center, and this forms the core. So the core is basically denser because it has iron, right? And the crust is made up of lighter materials. Okay, now oxygen is like crust and mantle. So like there is a lot of oxygen in the crust and mantle. Basically 50% of the weight of the crust and mantle is basically oxygen alone. I mean, that oxygen is not existing as an oxygen like an oxygen gas, but if it is existing as a part of the minerals or the rocks that are forming the crust and the mantle. So oxygen is very, very common. It's the most common element in crust and mantle. So almost in all the formulas that we'll see of rocks, a lot of them are oxides. So you have like oxides, generally you have like a lot of oxides, iron oxides, manganese oxides, copper oxides, tin, whatever, aluminium oxides. So in mineralogy, if you will take some time next semester, so we'll see like there's a lot of oxides. So there's a lot of also silicates. Now the silicate is also, the basic structure is SiO4, this structure. So there's also a lot of oxygen in the silicates. In the carbonates is also CO3. In the sulfates, SO4. So a lot of oxygen comes in. Okay. Now, this tetrahedral structure will come again and again and again. Now, sometimes two tetrahedrons will join like this. Sometimes some other tetrahedrons will come along and join like this. So there will be different kinds of silicate structures that we'll see. Sometimes they'll form chains, sometimes they'll form double chains, sometimes they'll form sheets, so on and so forth. Okay? Now, yes, you will find more iron-rich minerals or iron-rich silicates or oxides when you are closer to the core. And as you're moving into the crust, you will have less and less iron. So this is what we call, have you heard this term mafic and felsic? Mafic and felsic? So this is what it is. So mafic means rich in magnesium and iron. Mafic, ferrous, so that's the iron part, and mafic is the magnesium part. And felsic is like aluminium and silica. Okay? So when you have more felsic rocks, you have more silica and aluminium in them, like feldspars. And when you have mafic minerals like olivine, it can be Fe2SiO4 or Mg2SiO4, things like that. Those are more mafic. Now, when a rock forms from a certain amount of, like if a rock is forming by all these mafic minerals, so it becomes a mafic rock. When it forms from like felsic minerals, feldspars, silica, things like that, it forms a felsic rock. Okay. Now, as you move closer and closer, and as you move deeper, you get more and more mafic and then maybe ultramafic rocks. So when I use these terms, mafic and ultramafic, is basically, I'm talking about the SiO2 weight percent in the rock. So, say you have a rock. Now, this rock is made up of many different kinds of minerals. Minerals 1, 2, minerals N. Now, this mineral could be anything. This could be actually be a quartz. This could actually be an olivine. This can be feldspar, things like that. Okay. Now, quartz is SiO2. Olivine is a solid solution. We'll come to that. So it can be either Mg2SiO4 or Fe2SiO4. So it's like a magnesium silicate or an iron silicate, something like that. Feldspars have their own magnesium aluminium silicates or calcium aluminium silicates, things like that. But if we break down all these minerals, can we not break all these minerals as oxides? Or like the sum of oxides. So all these minerals can be actually broken down as a sum of oxides. We'll look into that. So basically, we can say that this entire rock has certain amount of MgO, certain amount of Al2O3, certain amount of SiO2, and all the oxides. So basically, any rock can be represented as simplistically as the summation of oxides. It is not actually a summation of oxides. It's basically made up of all these minerals. But mathematically, we can break down these things into oxides. And based on the SiO2 content, you can actually say whether we can classify them, whether they are felsic, mafic, and whatnot. So that is like mineralogy, petrology, that kind of thing. But this is where it stems from. Now, there will be okay. Let's finish this first and then I'll move. So you can have 4, you can have 6, you can have 8, you can have 12, things like that. And you can actually, so in this, what will be the shape? Octahedral, because we saw it was octahedral. For 8, it is called a cubic closed pack. Imagine like there is a cation sitting here. Imagine that the cation is sitting inside. And you have all these anions on, like touching it like this. But for simplicity's sake, I'm just representing the anions in here. So if you have cation in the middle, imagine it's inside a cube. So if I am the cation, I'm inside the cube, I can see the roof, and I can see those two anions and those two anions. And I can also see the two anions below me in the layer, those and those. So how many anions are there? 4 and 4. And I'm touching all of them together. It's very difficult to represent here, but this is called a body-centered. So this is called a body-centered. And it's a cube, so it's a body-centered cube. BCC. It's just the number of, based on my size, I now need 8 anions to support me. If I have 6, that's not going to cut it. I need to be tightly packed, and now I need 8 because I'm bigger. If you have become more big, then you'll have 12. And this is called like an edge-centered. So imagine something like a face-centered. Things like that can happen. Now, I'll not go into this, but I'm just trying to make you guys see this thing. There is a mathematical way of finding the radius ratios that will actually justify this mathematical positioning. So whenever the radius ratio is below 0.155, it is like a very small. So like 0.155 is like really small for this radius ratio. When the ratio is 1, what does that mean? The cation size and the anion size is same. As when you're decreasing the radius ratio, that means the cationic size is decreasing as compared to the anionic size. Make sense? Okay. I'm just writing these numbers here. There is a mathematical way of doing it. I'm not going to try that here. For 4, it is 0.225, 0.414 for both these. Okay? This is getting like really messy. But for 6, it is 0.414 to 0.732. Now this is from 732 to 1, things like that. And this is greater than 1. So if you have to find out whether a pair of cation and anion, what's their shape is going to be like, how the lattice will look like, you will just take the sizes of the cation and the anion, you will divide them, and if it falls between these numbers, it is more likely that it will form a tetrahedral shape. If it is bigger, then it will form. So it is if it is between 414 to 732, this falls under this. The thing is, these are ranges. These are not like concrete numbers, because mathematically it will be more like a concrete number. But there is a range in which things will try to accommodate itself. And why is that? Billiard balls are not accommodating. So why is the thing in here? Why there is this range in which things are getting pushed in or squished in? Why is that? Because the electron clouds are not billiard balls, right? They can be pushed, they can be squeezed in, right? And that is why there is a range in which these things can happen. Okay? Does this make sense? Like a little bit? Okay. Now, cations, like if you say you have the Na plus cation, so if you have Na plus, based on the anion or the number of anions it is surrounding, its size is going to vary. So Na plus will not have a fixed size because it's squishy. Depending upon the number of anions it is being surrounded by, it can like expand or contract its size a little bit. So imagine you want to fit into a crystal. So magma has erupted and it's cooling now and it's forming all these silicates because there's a lot of silica, Si, and a lot of oxygen. It's forming a lot of like these structures, and things want to fit in. So like sodium is coming, trying to fit in somewhere, magnesium is coming, trying to fit somewhere, all these kinds of things are happening. Depending upon, so if sodium sees these 4 coordination, and sodium is fitting into that 4 coordination, then the size of sodium plus ion will be about 1.07 angstroms. But if there is a bigger structure, like a 6-fold structure, 6-fold, like there is a, imagine, or like an 8-fold, something is forming, is like an 8-fold structure like this, and sodium wants to get inside. Not necessarily silica is forming that, because silicon oxides will always form this tetrahedral. Imagine there is something that is forming like a shape like this, and sodium wants to get in here. So it is basically has to expand its size a little bit because if it's smaller I can squish in, but if the room is bigger, so I'll like do this and then fit. If the room is bigger, I will try to do this and like reach the anions a little bit more. So I'm like expanding so that I'm in touch. But there will, of course, be a limit. So not everything will fit in everything. But sodium, when it forms a 4-fold, it will go to like 1.07 angstroms. When it forms a 6-fold, it becomes 1.1 angstroms. When it forms an 8-fold like this, it is 1.24 angstroms. Its size is increasing as it tries to fit. It's true for everything. So whenever you are thinking about the size of a cation, always think, how did you measure? Basically, so you're measuring the size of a cation based on its coordination number, because its size will change with its coordination number. Okay. All right. So this is an important concept. I like it. Okay, we are doing good. The effective electronics. So this will become like really important, because this will give you, basically this gives you an idea about like the shape and the size. So this is another a way of like thinking about the shape of like having some quantitative idea about the size. There's another very important thing which is called, it's called I call it charge density, because it's very easy to think about that. It's called charge density. What is mass density? Mass by volume? So what is charge density? Charge by volume. So it's basically the charge that you have by the size. It's kind of like gives you some idea about the size. So think about the radius. Because if you cube the radius, that becomes volume. Some people call this the ionic potential. I think this is a way too difficult term to think about. But if you see ionic potential somewhere, it's basically charge density. Okay, so when you have more charge density, do you think that particular cation, let's suppose, with a bigger charge density, will form stronger ionic bonds in here, or weaker bonds, higher charge density, greater charge density, stronger with the anions or weaker bonds with the anions? Stronger. Because it's essentially more charge per volume. So if you fix the volume, say this much, then you have more charge in here and there is an anion sitting there. So there will be more interaction. Versus in the same volume, you have a lesser charge. So there won't be that much interaction. So a greater charge density gives you a stronger bond. Okay. Now, these are the things that are happening in the ions. Okay. Now, when things will dissolve in solution, things will be different. So say you have NaCl and you dissolved it in water. The Na plus and Cl minus got separated, and the Na plus is just sitting there. What is going to happen to that Na plus? It's a plus that's sitting there. What's going to happen? It will attract negatives. Okay, so basically, when you have water present, these cations attract waters. So all these H2Os are coming in, getting attracted. Okay, which do you think is going to attract more? A cation with more charge density or less charge density? More charge density, right? So because you have more charge, basically. So you're attracting more waters. So when you have this cation, and you're having all these waters surrounding it, so I'm the cation, all these waters are surrounding me. Because if you have a cation, Na plus does not exist in water. It will always be surrounded by waters, and you will form a hydration shell around that cation. There's always a hydration shell. Now, when do you think that hydration shell is going to be more? More charge density or less charge density? More charge density. So when you have more charge density, then you're going to have a higher hydration. So will that cation be available to react if that cation is surrounded by all these hydration, all these H2O molecules?